The Earth's atmosphere is a massive system within which many complex processes interact. One such driver of these processes is the constant movement of air within the atmosphere, which conveys pollutants, moisture, pollen, and more across the Earth's skies. However, most of these things originate on the ground, so one has to wonder, how and why does air travel vertically as it moves? This is the question I'm going to answer today, and in doing so, we're going to touch on a lot of different subjects, so let's begin with the basics. Let's assume we have a mass of air, a parcel, if you will. This is just an arbitrary amount of air with a fixed mass, but not a fixed size. We also assume that this parcel does not exchange heat with its surroundings, and therefore its internal energy is constant. This parcel then behaves in a way that we refer to as adiabatically. Its internal energy does not change. So how does a parcel like this behave as it moves? If our parcel is forced upwards for any reason, it will expand. This requires work to be done on the surroundings, and the parcel must therefore cool in order to keep its total energy constant. The opposite happens if a parcel is forced downwards. It contracts and warms up. This is a pretty simple explanation, but the derivation is pretty complex, so we'll stick with this basic understanding for now. At any given height, the parcel will have the same temperature and the same volume. Now, this was all for a hypothetical parcel of air. We can plot the lapse rate as so and understand the general relationship between height and temperature for a dry parcel of air moved upwards or downwards by external forces. However, the atmosphere itself can have a much different relationship between temperature and height due to any number of natural processes. The differences between the atmospheric profile and adiabatic profile either enables or restricts vertical movement within the atmosphere. Let's see how. There are 4 types of atmospheric profiles. The first is an unstable atmosphere, shown here, in which the change in temperature of the atmosphere is more extreme than the adiabatic rate. This profile is very conducive to vertical movement. If a parcel originally at the same temperature as the atmosphere rises, it will cool slower than the atmosphere, or in other words, it will be warmer than the surrounding atmosphere. Warm air is less dense than cool air, so the parcel will continue to rise, accelerating upwards. Similarly, if a parcel sinks, it will be cooler than its surroundings and will just keep sinking. So, as you can see from this explanation, an unstable atmosphere will have a lot of movement from even a small amount of agitation. On the other hand, a stable atmosphere is one in which the change in temperature is less extreme than that of the adiabatic rate. A parcel that rises will be cooler than its surroundings, and it'll just move back down. The reverse is true for parcels that sink. In these conditions, air wants to return to its original state because it's warmer, and vertical movement is stifled. Now, a neutral atmosphere is one in which the adiabatic and atmospheric profiles match perfectly. Air will be moved by whatever forces they're subjected to, and won't really move up or down based on any other factors than that. So there is movement in these conditions, but it's pretty minor. Now we arrived at our 4th case, which is probably the most complicated. An inversion is any profile in which the atmosphere actually warms with height. This is a subset of a stable atmosphere, except, in a way, more extreme. These can trap air in low elevations, causing significant pollution problems. We see air will possibly begin to rise, but be stuck underneath the inversion layer and unable to rise further. This can be a big issue in certain cases, usually caused by geography, or weather patterns. There's a lot of different ways, but they can cause problems. So anyway, hopefully this was a helpful introduction to the mechanisms behind vertical movement and atmospheric profiles. As a closing thought, remember that it's the comparative slope of these profiles that matter, not the actual location of the atmospheric and adiabatic lines. A given parcel will be at the temperature of its surroundings before it's agitated, so all that really concerns us is the rate of change. There's no need to overcomplicate these graphs more than they already are. Just remember the trends that I've discussed, and everything will be just fine. Thanks for listening, as always.